Okay, and hello everyone, and welcome. We are continuing our discussion about the strength of the robot hand. This is part 3. There's introductory remarks in the YouTubes that I've created in part 1, so I'm not going to repeat them. The name of the YouTube is Give the Robot a Hand. Strength discussion part 1, and this is Give the Robot a Hand strength discussion part 3, and this is in Keyshot. This is sort of my pretty display imagery. This is always fun to look at. Everybody has their place where they put the pretty stuff. This is 500 megabytes in Keyshot. Here we have the robot fingers sticking straight out. We've curled them over into the sort of the thumbs up look. Here we have the hand grabbing onto a metal bar, and that's part of the strength discussion. And I'm going to talk about the cardanic joints and the hydraulic cylinders, but first I think we should discuss the frame that makes up the hand of the robot, or gives strength to the hand of the robot. And this is showing also the opposable thumb and the pinch position of the robot hand holding up the frame. And we'll switch over to SketchUp. Let's see what we have here. This is Kokino, an ancient megalithic observatory. So here is me trying to get a message out, and there's someone who listens to me. Back in here is the golden orb of funding. I don't think any funding will come to me. I just talk about the robot and the use of hydraulic cylinders. Here is Qualcomm, and here is Intel, and here is NVIDIA, Texas Instruments. I'm trying to get them to understand if you want to have a human mimicking robot, you need to use hydraulic cylinders. The electric motor rotary encoders, they work fine, but they're not going to let you create something that's the size of a human and can do what a human can do, because they're either too big, that's the problem with the hand, or they don't have enough strength. That's the problem with the robot. So let's take a look at SketchUp, and we will say goodbye to the pretty one. I do, of course, always like to remind everyone, I do have a YouTube channel. The name of it is Patrick Gray. I put all of my different discussions about the robot on that channel. I have a website. The name of the website is pistonrobot.com. You can go to the menu to discussions about a robot. Give the Robot a Hand is the page. On that particular page, I have links to all of the YouTubes that I've made about the robot hand. And I always try to put in there the remark about any physically real object might hurt somebody. If you're going to manage a physically real object, you should manage it in a way that is legally allowed and reasonable and safe. And if you can't manage it that way, my advice is do not create it as a physically real item. And we do have, I've already discussed what I think are the specifications that the robot hand should have. We're talking about the strength specification for this series of YouTubes. And we're back in SketchUp. We're talking about these articulations of the, we started at the very tip of the finger and we'll work our way back to the hand. These joints are, the pin for these joints is an M1.4 consideration of alloy 2205 alloy stainless steel bolt. They have a, for this configuration, their shear strength is 156 pounds. And we're going to look at, we've already looked at that and discussed it, but we're going to look at when these bolts are holding on to these parts. And here is this yoke of the ligament, the flexor ligament. We'll do a discussion on that. It needs to be able to develop 113 pounds of force in order to allow this finger to hold up 50 pounds so that the hand can hold up 200 pounds, because that's 50 pounds per finger times 4 fingers. And the way the calculation is done is, the question here is this yoke, and here is the polymer bushing inside of it. And so if the yoke is pulling too hard, then the bolt will pull through the yoke. And the question is, can the yoke tolerate that? And this section of the yoke is what needs to be torn apart in order for it to be declared to be too weak. And so that is a shear of this part of the yoke coming out. And the way you calculate a shear is you look at the surface area of these 2 points, the surface area of the green one and the surface area of the red one, and you multiply that times the yield strength. So the surface area is 0.006 square inches for red and 0.0069 square inches for green, multiplied times the yield strength is 390 pounds. And so this one is 448 pounds, but it's a shear, so it's half of that. This is the tensile strength. So in order to pull this out of here, you would have to have 830 pounds divided by 2. So it would need 440 pounds of force to break this yoke. And of course, that's for each side. So that would be 800 pounds. And the same argument can be made about whether the pin would pull out of the phalange. And again, this polymer insert is in here, and it's pushing down on this, and it's going to try to pull out this piece of material. So we look at the red area, 0.0053 square inches, and the green area is the same, so it's 344.5 pounds for each of them, and that would be here and here. And so that comes out to 688 pounds. That's the tensile strength multiplied times the 65,000, which is the yield strength of the 2205 alloy stainless steel. But it's a shear in order for it to push this out, so it would be half of that. So that comes out to be 344 pounds. So in order for this bolt to push through this phalange, you'd have to push down on it with 344 pounds of force. And remember, we're talking about a force of 50 pounds, so we're way inside of our specification. And just as a recall, we can show, I do the wrong one every time. There's 2205 stainless steel. Not the tensile strength, but the yield strength is 65,000 pounds per square inch. So that's where that number comes from. The other thing that we have to look at is we do have these bushings in there. Let's see if I can show you. See here, these are these bushings that are now remember, I take this metal, I put color in it so you can see the different parts, and I lower the opacity of it so you can see through it, so that you can see what's going on. And the real stuff would just be gray metal. You wouldn't see any of this. But here are these bushings, and that is so you don't have metal against metal, where this yoke is twisting on the bolt. And here where this phalange is, it's going to be held still, so it's not, what's going to happen is the bolt's going to turn. But you have this bushing in here allowing these yokes to pull on this without having metal on metal rotating contact. And so we got to take a look at these bushings and see what kind of forces are on them. And so now we're looking at force being applied by this yoke against this bushing. And remember, wherever the force is on the bushing, it's only going to be on half of it. Because if it's pulling this way, it's on the red side, but if it's pulling that way, it's on the green side. And so the green half of this bushing is 0.0067 square inches, and you can multiply that times the allowable pressure from the iGlide G1, which is 13,000 pounds per square inch, and that means you can put 87 pounds of force on this bushing. And the other side of the bushing, that's the part of the bushing that's being pushed on by the bolt. And the other side, the red side of the bushing, is pushing on the yoke, but that's even more force. And remember, we're only talking about 50 pounds of force for all of these places in between, and 113 pounds of force for this yoke that's connected to this flexor ligament. And that's going to be pulling with 113 pounds of pull, and the yoke is going to, the bushing is going to allow us to have 174 pounds. So it's actually enough ability for this iGlide G1 bushing to be the bushing for this use. And we can also look at the iGlide bushings. And this is the iGlide bushings catalog. And it tells you about their different materials. But they also get to a section of the maximum permissible surface pressure. And so we were using 13,000 pounds per square inch, which is the G1. But if you thought 87 pounds was a little bit low, there are some other. Here's one at 21,000. They're X material. 20,000, and somewhere in here, here's 29,000 for their TX1 material. So, and 15,000 here for the F. All of these different materials have different capabilities, and you pick the one you want. But technically, we have enough capability for this bushing to withstand the forces that we're going to put on it. And I did want to mention, I keep forgetting, this ligament that's doing the pulling is a braided aramid fiber rope. It's 3 millimeters in diameter. It's used in the world of high expense boat racing, yacht racing, and it has a breaking strength of 1,020 pounds. And it's 3 millimeters in diameter and almost no stretch. It's a braided aramid fiber rope, and so that's what I'm using here as the ligament for flexion and extension. And this is a 40 megabyte rendered PNG image of this hand curled over. We're thinking that this one, this one, this one, and that one probably need to be the T6 titanium bolt, perhaps these two. And then where this flexor ligament comes up and swings around, that one might need to be the T6 titanium. But all the rest of these bolts can be the 2205 M1.4 alloy stainless steel. They have nylon insert lock nuts on them so they won't come loose. And there's one other image here. And this is another 40 megabyte PNG image. It's showing the finger pulling with this pushing up with 50 pounds of force. So this is going to be pushing up with 50 pounds, but that's 25 pounds of force on each end of it. And we're going to move on down this finger to the metacarpal phalangeal joint and the cardanic joints and the hydraulic cylinders, but she is waving at me that we're out of time, so we're going to stop here and go on with another video.